Good afternoon, everybody. Welcome to this second session for the QEEE course on gears. So, in the last class, we did talk about the introduction to this topic. We understood in quite a few details why gears are necessary in the first place, and we spent the second half predominantly in understanding the different nomenclatures associated with the spur gears. So, we will take it up from here, that point where we left in the last class. In the last class, we were talking about instantaneous centers, about a higher pair mechanism. So, we will go that far, that we understood that for a higher pair mechanism, and gears are an example of a higher pair mechanism, we understood that the instantaneous center of a higher pair mechanism lies along the common normal. Where exactly is it lies, that on the common normal is unspecified, that is determined by the exact type of motion that the higher pair involves in. So, today we will our first objective will be to arrive at the instantaneous center of the mating gear tooth. Mating gear tooth, as we understood through yesterday's discussion, is an example of higher pair mechanism, but we wish to specify exactly for a mating gear tooth where is the position of the instantaneous center. So, as per our discussion yesterday, we understood that instantaneous center has to lie along this common normal of the mating gear tooth. So, what you see in the figure here is just an example of two arbitrary tooth of a gear. So, the gear itself has not been drawn, and the gear tooth profile is also pretty much peculiar. It is not one you would find in practical application, but that is just to make things arbitrary at this stage, because at this stage we have not yet come to the result that the gear tooth should be a particular should have a particular geometry. So, we keep the gear tooth geometry arbitrary, which is why this drawing looks pretty much peculiar on first sight, but the derivation is pretty much rigorous, because we see that this derivation is true for arbitrary tooth profiles. So, here on these are the two gear tooths which are basically attached to the gear body. So, if you look at it from first principles, there are three different rigid bodies which are there in the current discussion. One is the frame itself, that is all motion will be with respect to the frame of the motion, and that has been numbered as 1, that is the default number for the frame. We have this body numbered as body 2, and the other gear, the smaller of it, is numbered as body 3. So, as we know, the two gears are rotating with respect to the frame, and that is through the connection between each of the gears and the frame is through a revolute joint. So, this is the revolute joint which actually is the instantaneous center between the frame and the gear. So, as I said, the nomenclature would be, the gears will be denoted by 2 and 3, and 1 is the reference for the frame. So, therefore, the instantaneous center of the gear 2 with respect to the frame, which is denoted as I12, is basically the revolute joint which connects the gear to the frame, and that is what is shown here, I12. And similarly, I13, which is the instantaneous center of the gear which is taken as body 3, and that instantaneous center of instantaneous center between body 3 and body 1, which is the frame, is exactly the revolute joint which connects these two bodies. So, I13 happens to be located here, I12 happens to be located there where I am pointing my mouse. So, these two instantaneous centers are easily determined. I23, which is 2-3, remember, are forming, the body 2 and body 3 are forming a higher pair within themselves, and as a result I23, or the instantaneous center between these two bodies, as per our discussion yesterday, will lie somewhere along the common normal. Where exactly it lies was not specified in yesterday's discussion, but we will do that today. But to specify where exactly it is located, we invoke what is called the Aronholt-Kennedy theorem. Again, this is a result which comes from your basic discussions in mechanism. So, please look back at this Aronnaud-Kennedy theorem and the proof of it, but the essential result of Aronnaud-Kennedy theorem is the following. The Aronnaud-Kennedy theorem states that when you are talking about the relative instantaneous centers between three bodies, then all these three relative instantaneous centers have got to be collinear. So, in this case, the one that we are dealing with, we had exactly three bodies, two of them are the two gears and the third is the frame with reference to which the motion is taking place. So, there are three bodies, and by Aronnaud-Kennedy theorem, the relative instantaneous centers among these three bodies, and obviously since there are three bodies, there are three relative instantaneous centers between them, that is namely I12, I13 and I23. So, what Aronnaud-Kennedy theorem gives us is that these three relative instantaneous centers must be collinear. So, we have already found out I12 and I13, these being the revolute joints which connects the gear with the reference frame. Therefore, the Aronnaud-Kennedy theorem says that the third instantaneous center I23 will have to lie along the line joining I12 and I13, right. That is what the Aronnaud-Kennedy theorem statement gives us. We have also figured out from our discussion yesterday that this instantaneous center I23 has also got to lie along the common normal. So, therefore, to satisfy both these conditions, we must have the instantaneous center to be located at the intersection of the common normal between these two gear tooth and the line joining the two other revolute joints or the shaft centers. So, therefore, this point of intersection between these two red dotted lines, as you can see here, is the instantaneous center between the two gears. But how is it that the instantaneous center helps us in our kinematic analysis? To answer that question, let us look back at the property of instantaneous center. The property of instantaneous center states that whether you assume this point P or I23 to be a point embedded in body 2 or a point embedded in body 3, in either case you will be able to conclude that whether it is in point 2 in body 2 or in body 3, either ways it will have the same velocity, right. If it is in body 2, it is the body 2 has an angular velocity of omega 2. So, if I assume this point P is embedded in body 2, then it will have a linear velocity which is omega 2 times I12P, because remember in this body is having a rotation about this point. So, every point which is embedded in this body or in an extension of this body should have a linear velocity which is given by the product of the rotational velocity times the radius vector. So, with that argument, the velocity of this point P will be the angular velocity multiplied by this radius vector, which is omega 2 equals to times I12 times P. Similarly, if I argue that this point P is now embedded on body 3, then the velocity of this point P should be omega 3 times I13P. The distance I13P is precisely this distance, the radius vector about which the body is rotating. So, therefore, by property of instantaneous center, which suggests that either ways the velocity should be same, we have this equality, which basically means that we now have a rule by which we can assign what is the velocity ratio between these two objects. Between these two bodies, when there is motion transfer happening, the motion transfer ratio omega 2 by omega 3 is given precisely by this quantity. And that is what brings up to the fundamental law of gearing. Remember, in yesterday's discussion itself, we understood that the primary objective of having a gearing arrangement is to ensure a constant velocity ratio. That is, the ratio of omega 2 by omega 3 has to be fixed for all times. So, that essentially now means through this analysis omega 2 by omega 3 can only be fixed if this point P is fixed, because I12 and I13 is fixed. This is fixed with respect to the reference frame. Therefore, these 2 points does not move. The ratio of omega 2 by omega 3 can therefore remain constant if and only if the point P does not move during the course of engagement. And this is what is called as the fundamental law of gearing. The fundamental law of gearing states that the velocity ratio between these two gears will be fixed if and only if the pitch point, or this point P is basically called the pitch point, is fixed. So, that is where we are coming at. So, for transmission of constant velocity ratio at all times, the common normal between the mating gear tooth must intersect the line joining the gear centers at the fixed point. This is exactly what we have proved. The line joining the gear centers is this red line, and the common normal is this one. The intersection between these lines is the instantaneous center between these two moving bodies. The instantaneous center between these two moving bodies has this nice property that the velocity ratio is related to this, the ratio of these two distances, and therefore, if you have to keep the velocity ratio constant, you have to as well keep the ratio of these two distances constant, which essentially means that the point P has to be fixed. It cannot happen that as the engagement is taking place, that this point P keeps moving, or in other words, if the common normal keeps changing its orientation and intersects different points on this horizontal red line, then obviously the point P will move during the engagement, and if that happens, the disaster would be that the velocity ratio will not be fixed. So, even if the engine supplies a constant velocity, the output of the transmission will have a fluctuating velocity, which will really be very detrimental from different perspectives like ride comfort, vibration, and so on. So, you do not want that to happen, and because of that reason, we are demanding that we have this condition of fundamental law of gearing satisfied. Okay, so the fixed point of intersection between the common normal and the line joining the gear centers is called the pitch point. So, that point P, which we referenced in the previous slide, is called pitch point, because if you look at it from a different perspective, if you look at it from the perspective of pitch circle, then basically the same motion transfer can be obtained by using two friction discs of radius I12 P and of radius I13 P. So, if these two radiuses are taken of a equivalent friction disc, it will be a completely kinematically equivalent picture. So, in that respect, this point P is the pitch point, because pitch point, as we defined in the last class, is the point of tangency of the two pitch circles. So, in this respect also the nomenclature of pitch point makes sense. So, as I said, for transmission of constant velocity ratio at all times, the pitch point must remain fixed. This is very important. If that does not happen, then that ratio of omega 2 by omega 3 will keep changing, and thereby it is detrimental for the operation of the gear. And the reason why the tooth profile geometry has to be very carefully selected is to maintain this condition. If you arbitrarily select some tooth profile, maybe you in a simplistic manner you select that to be a straight line. If you select the tooth profile to be straight line, and I have seen that in certain mechanical engineering festivals, I have seen logos where the gear tooths are shown sort of simplistically as straight, but such straight gear tooth profile will not be able to work as a good transmission system, because the fundamental law of gearing will be violated. Right. So, arbitrary tooth profiles will not be able to maintain the condition of fundamental law of gearing, which demands that the pitch point should not change, and pitch point by its definition is the line joining the common normal between the two mating gear tooth and the shaft centers. Right. So, even if the common normal changes, it should be ensured that the point of intersection of the common normal does not the point of intersection of the common normal with the line joining the gear centers should not change, right. The very special kinds of tooth profiles which are able to satisfy this condition as demanded by fundamental law of gearing is going to be called as conjugate tooth profiles, and there are the tooth profiles that we are going to talk on from here talk from here on are going to be these conjugate tooth profiles. It turns out involute tooth profiles are conjugate, and that is what we are going to study. There are other tooth profiles also which are conjugate, but we will see predominantly the gears are made as involute tooth profile. One reason for involute tooth profile is that we will see that the involute tooth profile is always able to satisfy this condition of fundamental law of gearing. There are other conjugate tooth profiles, for example, cycloidal tooth profiles are also conjugate, but they have the involute tooth profiles have very many other advantages other than this fact of satisfying the fundamental law of gearing. There are other advantages also, and we will talk about them one by one, but the takeaway is that the involute tooth profiles are widely used in application, not just for the reasons of fundamental law of gearing, but also it is easy to manufacture, and I will talk about that aspects also. Because of that reason, involute tooth profiles will be predominantly used during all the applications of gearing, and they are the ones which are like produced in mass manufacturing of gears. And when you have that, you will be able to appreciate that we need to study involute tooth profiles in greater detail. So, we will come to the point as to what is an involute and things like that, but just to give you a feel of how involute gear tooth profiles are actually able to satisfy fundamental law of gearing, let me demonstrate to you a quick model which I have brought in from our lab, and hopefully you will firstly get a feel of what I am trying to say by meaning that involute gear tooth profiles follow the fundamental law of gearing. So, let me explain that on the model, and then I will come back and do the rigorous mathematical derivations in due course. So, I will now demonstrate the model to you at this stage. So, what you see here are gears, except for the fact that we have not cut out tooth for the entire gear disc. For there is only one tooth that is cut out. These are just cut out for our demonstration purposes. So, now you can distinctly see that a gear tooth profile has been cut out. You can see that this is the tooth profile on one side of the gear. We have not cut out on the other side, right. Similarly, on this disc you are able to see a tooth profile which is this. It so happens that it is involutes, but we will come to what is theoretically what is called the involute and the mathematical definition of involute and all that. But first let us understand how does the engagement take place, right. So, this is the engagement that is happening between one pair of gear tooth, right. So, if this is the driver and this is the driven, this is how the gearing action will take place, right. If you can carefully note what we have as this white line, the point of contact you can see is moving on this white line, right. This white line, you can see this white line going through. I will just move the gears once more. So, there is a white line which goes to white oblique line, right. So, this is the point at which the common point of contact, the point of contact during the engagement always stays on this white line. Just observe as I am moving the gears, the point of contact always stays put on this white line. Similarly, if I do it the other way around, the point of contact you will be able to see always lies on this white line, right. So, in other words, the common normal which obviously has to pass through the point of contact is precisely this oblique white line, right. So, what we have shown through this demonstration is this, that the common normal during the process of engagement, which is this white line, is actually not changing, right. The fundamental law of gearing demanded that the common normal always intersect the shaft center at a fixed point. Which is the shaft centers here? The shaft centers are here. So, the fundamental law of gearing demanded that the common normal during the course of engagement should always intersect the line joining the shaft centers at a fixed point, which is called the pitch point, which in other words it simply concisely means that the pitch point should not move. This is exactly what is happening in this case, that if you see carefully, this is the point P which has been marked as the pitch point, right. So, always the this vertical line is that you see barely see here is the line joining these two shaft centers, right. And therefore, during this entire course of engagement, the common normal between the two gears remains same. it always intersects this line joining the shaft centers at a fixed point, because common normal is fixed, line joining the shaft centers is fixed, their intersection which happens to be the pitch point is fixed. So therefore, the pitch point has remained fixed owing to the fact that we have got a very specifically made profile on the gear tooth. This is an involute profile gear tooth. We could have demonstrated this also with other gear tooth profiles, but we kept it specific to the involute gear tooth profile, because as I said, that is the most commonly used tooth profile in industrial application, because not only it satisfies fundamental law of gearing, there are other advantages also which I will talk about. But at this point, this demonstration should make it clear to you that this fundamental law of gearing is getting satisfied in in this manner. This has been demonstrated through a model, but now we will come back and we will try to analyze a bit more theoretically, a bit more rigorously in some geometric fashion that why is it that the involute tooth profile is able to satisfy the fundamental law of gearing. This is just an experimental demonstration that yes, it does satisfy the fundamental law of gearing. Now we will get back to the theory once more. We will return to this model to explain few other things about gear geometry. Okay, so coming to what is an involute. So the definition of involute is pretty simple. If you take a taut string and unwind that taut spring, any point on that taut string will generate a involute. So the locus of any point on a taut string as the string is unwound from this circle is going to generate the involute of a circle. Actually, very specifically we should call this involute of a circle, because the string is unwound from a circle. But when we say involute without any qualification, we simply mean that it is involute from a generated from a circle. So the technical definition of an involute is thus that the locus of any point on the string as it is unwound from the circle will generate an involute. The involute gear tooth profile satisfies fundamental law of gearing. I have just demonstrated that to you through this cute experimental setup, but I will also try to prove this to you from a first principle theoretical argument from a geometric standpoint. And towards that end, and before I do that, there is one more definition. The circle over which this string was winded up, that circle is known as the base circle. So circle over which the string was initially winded up and now it is getting unwinded as the involute is getting generated, this circle is known as the base circle. So just to repeat myself, there is a string which is initially taut around this circle. This taut string is being unwound. As this string is being unbound, any point, for example this point which has marked as T in this string will generate a curve, and that curve is known as the involute curve. The circle itself over which the string was initially wound and in the process of unwinding has generated that involute curve, that circle is called the base circle corresponding to the involute. Okay, so these are the geometric terms that we will have to get ourselves acquainted with. Now to re-establish this idea that to re-establish this point that the involute tooth profiles actually satisfy fundamental law of gearing, as I said, I will use a different proof, not relying on this experimental model, and that proof is based on what is called the cross belt pulley analogy. So the cross belt pulley analogy goes in the following fashion. The cross belts, as you know, are like an internal tangent between the two circles. So what we have here is two pulleys which are connected through a cross belt. So in this case, the bigger pulley is rotating in the clockwise direction and the string is being wound around this bigger pulley. So in the sense of the pulley, this is the driver pulley, and in the smaller pulley case, the string is being unwound, right. So what we would try to imagine here, and please be with me in terms of visualization of this procedure also, I will show you a video to help you to visualize, but let me run through the lecture first. So, if we take something like a pencil on any point uh, on this belt, this cross belt, we attach a pencil, right. As the mechanism is operating, this pencil will obviously trace out a straight line on the plane of the reference frame. So, if we have a paper attached to the base, as this mechanism is moving, that paper, we will see on that paper there is a straight line, because the belt particle on the belt is actually moving on a straight line with reference to the inertial frame, right. So, with reference to our body frame, the particle is simply moving in the straight line, which is what we see in with our naked eyes. But now let us tax our imagination and say that instead of fixing the paper to the reference frame, we are actually fixing the paper onto the one of these gears itself, or one of these discs itself. So, the paper this time is not attached to the inertial immobile frame, it is not attached to the stationary frame. The paper itself is moving, and it is moving in the same manner as one of these pulleys. So, for example, if the paper is attached to the smaller pulley, then this mechanism is allowed to operate, then the question is, as the mechanism operates and you have fitted a pencil in, at a fixed point of this belt, then the question is, what is the curve that will be traced out on that piece of paper now? A little bit of thought and hopefully a video demonstration will make it clear that it will trace out an involute, because if you think carefully, what is happening is that this belt is basically like a string which was initially wrapped up into this circle. What the other pulley is doing is that it is unwrapping this string, and as we know, the unwrapping of the string will generate an involute with reference to this circle. So, therefore, the graph that will come out this time will be an involute, and this is what is being shown in that little portion that you see here. Similarly, on the other pulley, if I attach this same piece of paper, what I will see is that on this other pulley, it will generate the involute from the other side, that is, from the smaller pulley it has generated the involute from the circle outwards, whereas with respect to the larger pulley, the involute has been generated from the outer periphery inwards. So, this is what happens at an early instant of time. If the motion is recorded after a certain lapse of time, in such a case this point would have moved here, and the involute, as you see, is on the smaller disc is going in the outward direction, whereas the involute profile which is coming onto the larger gear is getting generated inward. So, one involute is getting generated outward and the other involute is getting generated inwards. The involute corresponding to this larger gear, larger pulley I should say, because this is a cross belt pulley analogy. So, the driver pulley is, on the driver pulley the involute is getting generated inward, whereas on the driven pulley it is getting generated outward, because this larger pulley is the driver pulley which is sort of forcing the unwinding from the smaller pulley, right. But I will show a video of this illustration of this idea such that you get a better hang of this visualization. But before I do that, another point that I would like to iterate. Please note, during this entire course of motion, the common normal between these two profiles is nothing but the cross belt itself, right. The cross belt is the common normal. The point of contact always is basically that pencil. The point of contact associated with these two profiles is basically the pencil which you had attached and which is generating these two curves. So, the point of contact is moving on the on this line of the belt. So, basically that belt is the common normal associated with these two pulleys. So, what we have done is that as the involute is getting generated, we have shown you that the common normal of these two involute pairs is basically that cross belt. which is actually not changing during the entire course of engagement. During the course of engagement, the point of contact is changing, it is going outwards with respect to the with respect to the smaller pulley, and it is going inwards with respect to the larger pulley. But the point is that the point of contact with respect to the stationary frame is nothing but the belt itself, which is not changing. So, therefore, the common normal is nothing but the cross belt itself, which is not changing its orientation. So, therefore, the common normal is held fixed during the course of engagement of two involute tooth profiles, which is exactly what we have seen even in our experiment a few moments ago. So, therefore, we come up to this very important conclusion that the common normal has not changed. So, this is exactly what I have told you. So, the point of contact between the involutes always will lie on the belt, which means the belt is the common normal between the involutes, and the common normal therefore did not change during the course of engagement of this involute, which essentially means that the pitch point did not change. So, what we will now do is from the pulley picture we will come back to the gear picture. So, instead of this pulley picture, now if you assume that identical force transmission as this belt pulley drive is happening between two gears on which there has been this sort of involute tooth profile that has been cut out. So, if you cut out exactly these tooth profiles on gear, and if you push, or rather if you apply a suitable torque such that identical motion transfer takes place, then it is going to be exactly the same. So, that is why we refer to this as a cross belt pulley analogy. From the pulley picture, belt pulley picture, it is very easy to identify that the normal did not change, and the motion transmission will not change if we have exactly the same sort of force transfer, torque transfer that is taking place. So, that can be attained. So, this is the last step of the analogy where we say that the identical motion transfer can be obtained if the belt is replaced by involute tooth on the pulley. So, this is how we will create a positive drive. By positive drive, as I said yesterday, one element has to apply a force or a torque to the neighboring element, only then the drive will work. It is not based on any frictional effects which is true for friction disc or even for belt pulleys, right. So, in the last step of the analogy, we just replace this belt pulley system with discs with toothed wheels, the tooth profile being exactly the same as being traced out from the belt pulley analogy. We already have seen what is the profile of the of these curves which get traced out. So, exactly with the same curves being traced out, if we run this belt pulley system, we will be able to get exactly identical motion transfer with the same forces that were transferred by the belt. If we apply the same forces back, we should get exactly the same motion transfer. So, that completes my description of cross belt pulley analogy, and the reason why the cross belt pulley analogy is important, it clearly demonstrates that the common normal remains fixed during the engagement, which means that the intersection of the common normal and the line joining gear centers, this is the line joining the two disc centers or shaft centers if you may call, that obviously will not change. What we have proved is the common normal, which happens to be this dotted line, will also not change, which means that the pitch point always remains same during the course of engagement, which is exactly what is required as per fundamental law of gearing. And since this tooth profile now is proven to satisfy the fundamental law of gearing, without further ado we can say that this tooth profile will maintain a constant velocity ratio during the entire process of engagement. So, that is the proof that I wanted to go through. I could sort of sense that this is demanding in terms of the visualization. So, what I will do is that I will play out a video for you. This video has been taken from YouTube. The channel is called Kinematics with Microstation. It is authored by Mr. Ujjwal Rane, who happens to be an IIT Madras alumnus. So, we had some friendly interactions also in the past. So, this is a very nice channel in which lots of mechanisms are animated, and hopefully the students will get a lot of useful visualization aid to understand different finer concepts in the geometry of mechanisms. So I am playing this out for you now. It's about a 5-minute video, so I'll let this video run, and this video should possibly reinforce your visualization of this cross belt pulley analogy as I have discussed. So I'll play out this video now.
Here we are going to devise a drive to transfer motion under two conditions. Number one, the velocity ratio should remain steady all the time, and number two, there should not be any slip under any load condition. That is, the drive should be positive. Let us start with the first condition, the constant velocity ratio. It is typically made by belt drives like the one shown here. It consists of two pulleys connected with, say, a cross belt. Now this drive gives us a constant velocity ratio, but at higher loads there could be slip. That is, the driver pulley may roll, but the driven pulley may not roll to the expected extent. And this happens because we are using a force which is not very reliable, the force of friction, which cannot increase beyond a certain limit. So instead of using this force where the motion is tangential, let us use a force where the contact is normal. So a direct push is applied. That is the force of contact or the normal reaction. So we are going to replace the tension in the belt by normal reaction. For that we will need a contact between the two pulleys. Since they are far apart, we will have to extend them, and the extension should be such that the contact should be retained even after the pulleys roll. There is a simple trick to achieve this, and that is, we will take a point P on the belt and put a pencil there and draw a shape or a profile or an extension on both the pulleys simultaneously. Since both these extensions or profiles are drawn by a common pencil, they will definitely make a contact at that point, and so the contact will be maintained. To understand what kind of profile this generates, let us concentrate on any one of these pulleys and use this setup. Over here, this is the pulley. To it, a cardboard is attached on which we can draw. Instead of belt, we have this inextensible string, and on it there is a pencil. Let us set this in motion, and you can see as the string unwinds and the pulley rotates, relative to that pulley on the cardboard, a curve is getting traced. Now by definition, a point on an inextensible string getting unbound from a circle traces an involute. So what we are getting here is an involute. Now as the string is getting unwound from one pulley, it is getting wound on the other. And it doesn't matter whether we are winding or unwinding, relative to the pulley, a point on that string will always trace an involute. So we are not only tracing an involute on one pulley, but relative to the other as well. And these two involutes will always make a contact. So this is how it looks. So there is a green involute on green pulley, and the red one is getting traced on the red one, and they are always making a contact, and a direct push is applied, thereby the motion is transferred. So there is no chance of slip. So we are not only getting a constant velocity ratio, but we are also getting a positive drive. The best of both worlds, and now we can call this a gear. And because we are using involute profile, this gearing is called involute gearing. We must bear in mind that these two profiles work together as a team to give us a positive drive with constant velocity ratio.
Okay, I think I'll stop here. The last 1 minute is possibly not relevant, but I welcome you to look at these videos when you do get time, because these videos you will understand are quite useful for your visualization. Okay, so with that, let us return back to the slides. So hopefully with some understanding of the involute geometry, we are now in a position to understand the gear geometry a little better. So we will introduce a few more nomenclatures now associated with the gear. So here what you see is the involute gear geometry. So there are two additional concepts which come into being. One is the base circle. So base circle, as we have understood, is that this involute gear tooth profile must have been generated by unwinding a string from a certain base circle. So accordingly, we have the base circle of a gear to be that imaginary circle based on which this involute gear tooth profile has been generated. So that's the base circle for you. So any engaging gear tooth gear pair will have the base circles, just like there is pitch circle, there is base circle also, but both base circle and pitch circle are imaginary circles. There is no circle that you can directly see with your naked eyes and identify that this is a base circle. But remember, the base circle is very important because this involute tooth profile must have been generated by unwinding certain string from a certain circle, right, and that circle is called the base circle. And there is also another important concept, that of pressure angle, as some of you were asking yesterday. So as we understood that when there is a gearing action, essentially one gear pushes the other, and the push will come in the direction of the normal, in the direction of the common normal between the two gears. So in this case, as is shown in this picture, you can understand that these two pair of teeth which are in contact will have a common normal, which is this, right. Fortunately for involute gearing, the common normal does not change during the course of engagement, but you can understand from the perspective of transmission of forces, the normal force is the major force which is getting transmitted even if there is no friction in this process. That is why it is called a positive drive. It does not depend upon on any friction aspects for this mechanism to work. It does not work on the no slip condition principles. It works on the principle that one of this gear is pushing the other, and the push obviously is in the normal direction, right. So the normal direction happens to be this. So the force that is getting transmitted between the gear pair is aligned along the common normal, right. So you would like to have a reference for the direction of this force transmission. So the direction of this force transmission is referenced with respect to the tangent to the pitch circles. Remember, the pitch circles are just at the in the condition of tangency. The two pitch circles, as has been shown here, are touching at one point, and this red line, the red arrow, is a common normal to the two pitch circles. But the common normal to the two pitch circles is not the direction along which the force transmission is taking place. The force transmission is taking place along the common normal of the two teeth which are in contact, right. The two teeth, when they are in contact, the common normal happens to be this, and this common normal does not change during the process of engagement. So the angle between this common normal of the two gear tooth, two involute gear tooths, is the angle of the common normal with reference to this common tangent is called the pressure angle. So the pressure angle is the angle between the common normal between the gear tooth and the common tangent of the two pitch circles. But the common normal, as we have seen, is also the internal common tangent of the two base circles. So therefore pressure angle can also be said as the angle between the between two tangents. One tangent is with respect to the two pitch circles, and the other tangent is with respect to the two base circles. So this is the common normal, which is also the internal tangent to the two base circles, and the angle is between these two lines. One is the common normal, which is also the internal tangent to the base circles, and the other is the common tangent to the two pitch circles. So this angle is called the pressure angle. And we have a very interesting relation between the base circle and the pitch circle. So the base circle pitch circle relation goes in the following fashion. It can be shown that the base circle is the pitch circle times cosine of the pressure angle. So if you look carefully, or maybe I can draw this once again here. These are the two pitch circles, and these are the two base circles. It is shown in an exaggerated fashion such that the drawing is clean. So this is the common tangent to the two base circles, and this is the common tangent to the two pitch circles. So this is RP, which is the pitch circle radius, and this is RB, which is the base circle radius, and this is 90°. So what happens is that this angle is phi, which is the pressure angle. This is also 90°. So that means this is 90 minus phi, which means this is also phi, right? So therefore you have a triangle, right angle triangle between RB and RP. So therefore from this geometry it is clear that RB is equals to RP times cosine of phi, right? So it is just from elementary geometry that you get this relation. That is also proved here, but the drawing looked a little bit cluttered, which is why I had redone it. Let me once more demonstrate this aspect to you in this model. So as I have been saying that the common normal is this white line. So the force that is getting transmitted between the two gears, as I am rotating this gear, there is a force which is getting transmitted onto this body, that is why it is rotating, right? The force transmission has to occur at the point of contact, and even if I assume that there is no friction between these two bodies, the force will be along the common normal, which will be exactly along this white direction, this direction here, right? So this is the common normal, which also happens to be the tangent to the base circle, and this angle, which is actually indicated as psi in this model, but we are calling it as phi, this angle will be called as pressure angle. Okay, so that's from the modeling perspective. So now we'll come back to the pressure angle. I think all that has been explained. Yeah, so what you can understand is that the force that is getting transmitted is along this direction, which is indicated as I am scrolling the mouse, but only a component of this force is going to act along this direction, which is responsible for the torque. So the torque producing component will be only the cos phi component. So the F cos phi multiplied by RP is what is going to be responsible for the torque transmission. So you lose the component of a force. The force that is being transmitted being in this direction, one component of it is towards the shaft direction, and the other component is perpendicular to the shaft. So this component, which is vertically aligned and pointing in the red direction, is responsible for the torque. So the F component, which is acting here, you take cos phi of that, and this component will get multiplied with the radius and give you the torque transmission. So the torque that is getting transmitted is RP times F cos phi, RP being the pitch circle, which is basically this distance. OG to this red dot is the pitch point. So this distance is RP, and RP times F in along the vertical direction in this picture is going to be the torque that is getting transmitted. The other component is going to simply go to the shaft, and it will cause a shaft deflection. So the other component is F sin phi. F cos phi is responsible for the torque, but F sin phi, the component which goes horizontally, is actually going to get transmitted to the shaft itself and is going to cause a shaft deflection. So obviously, as we said in our discussion of the friction disk also, you would like to keep this component at the minimum. It so happens that the pressure angle that are used in general will be of the order of 20°, 22.5°, at the most 25°. right. So, you will keep sin phi component down for this reason, that if you have a large sin phi, it essentially means that you are wasting a lot of the force in the sense that it is not able to transmit the torque. You obviously want the torque to get transmitted. Rather, if sin phi component is larger, then it will cause a large force to be transmitted to the shaft, and the shaft being a beam like member is flexible member, it will actually bend, and once it bends, then there is a chance that the engagement may not happen properly between the two gear tooth. So, therefore, we will keep the pressure angle to be small, and the standard pressure angles that are usually used is 14.5 degree, 20 degree and 25 degree. And as I said yesterday, the pressure angle together with the module determines all the geometric diameters and geometric dimensions for the gear tooth, and these have been arrived at after extensive simulation experimentation over the years, and therefore, these dimensions are taken as standard. Obviously, one can try to improve this, but such a improvement would require a more exhaustive study, which at least in the context of this course is not feasible. We will take these dimensions to be like standard dimensions derived on the basis of experimental studies, and further research applications also have proved that these are the optimal choices. We will just stick by it. How they have arrived at these dimensions is a discussion which we will not get into. We will simply convince ourselves that these dimensions have been arrived at mostly from strength calculations perspective, and keeping in mind that whatever we have the kinematic objectives will be fulfilled none the same, and the strength qualifications will be met, and also the manufacturing is will be satisfied if all these conditions are taken into account. So, as we have said that there are a number of advantages of involute tooth profile. The first one, which we have talked extensively, is that involute tooth profile satisfies the fundamental law of gearing. Constant velocity ratio can be obtained as a result of this involute gearing arrangement. What we have seen is that the common normal does not change during the process of engagement, which means the common normal essentially fixed. That in turn means that the pressure angle is also fixed during the engagement, because pressure angle is basically the direction of this common normal with respect to the tangent to the pitch circle, and since the common normal has not changed, pressure angle has not changed. There are other profiles, for example cycloidal profiles, wherein the common normal does change during the engagement. It changes, but it happens to still intersect the line joining the gear centers at the same point. As a result, the first criteria is satisfied even for cycloidal gear, even though the common normal is changing, it is passing through the same pitch point. But in a cycloidal gearing arrangement, what will happen is, because the common normal is changing, the pressure angle will not remain same during the process of engagement, it will change, and once it starts changing, both of these components will start changing, f sin phi and f cos phi also will change. So, that can cause a lot of problem associated with dynamics, associated with vibration. So, therefore, you will not get a smooth operation of such gearing arrangement. That's one reason why involute gears are supposed to have a smoother action in comparison with any other conjugate tooth profile also. Again, another very important reason why we go for these involute tooth profiles is that they are very robust. What will happen in practical situation is that there will be assembly related inaccuracies. You may have designed the gears to be operated between two shafts which are placed between which are placed at a certain distance apart, but you can understand during the assembly process this distance will not be maintained, there will be slight deviations to this distance. It so happens that involute gearing can actually accommodate these slight changes in the assembly related inaccuracies, and the only change that will happen is in the change of pressure angle. Nothing else will sort of fall apart, everything else will work, the fundamental law of gearing will still be satisfied. It is only that the pressure angle will change by a little bit, and I have a small example worked out for you, which I will show immediately afterwards. So, to show how the pressure angle changes because of a slight change in the distance between the shaft, and you can understand the distance between the shaft will change due to manual assembly processes, for example. The fourth advantage of this sort of a gear is that while we are looking at involute tooth profiles, we must remember that the actual manufacturing process of these gear tooth profiles will be done on the basis of, let us say, a rack cutter, right. So, if you recall, there is a rack and pinion arrangement that we have talked about in the last class. In the rack and pinion arrangement, we understood that there is, when the rack will have a linear motion, the gear will have an angular motion. So, essentially, if a rack is allowed to sort of have a reciprocating motion, that is oscillatory to and fro motion, then accordingly the gear attached to it will have a oscillatory angular motion. So, this is something similar which is done in gear manufacturing process, and you can look up videos in gear manufacturing processes. Kinematics with Microstation channel has nice videos of gear manufacturing also. We are not going to talk about gear manufacturing in details in this talk, but suffices to say that the rack cutter will the rack associated with an involute gear. You know, there is an involute gear which is supposed to have angular motion. The corresponding rack will also have a certain tooth. It turns out that the tooth corresponding to the involute gear will be straight tooth. In a rack, the tooth of the rack corresponding to an involute gear will be straight tooth, and as such, if you have a rack cutter which actually does this cutting operation on a gear blank, then this rack cutter need to be only straight tooth. You can understand making a rack cutter which is anything other than straight tooth will be very difficult, because cutters are very difficult to machine and very difficult to make in the first place. So, making the cutter available will, a rack cutter available will be very easy in this case as compared to any other case, because it so happens that the cutter associated with an involute gear tooth profile has, the rack cutter associated with the involute tooth profile has only straight tooth. It does not have any complicated profile, even though the profile in the gear itself is not straight, but the rack, the corresponding rack will have a straight tooth, and this can be very handy and very advantageous in the process of manufacturing of gears, because rack cutters become easily available for you, and then you can use these rack cutters to manufacture the gears in mass production processes. Okay, I will come back to this example, but before that maybe I can take a quick break and open myself up to various questions. I see some questions are already posted, so we will take 5 minutes or maybe 10 minutes time to answer few questions that you have. SUCET is asking, if the centers are disturbed, then what will be the effect on involute profile? The effect will be nothing other than a minor change in pressure angle, right. The base circle remains the same, the pitch circle will be slightly changed, the pressure angle will be slightly changed, nothing else will happen. Fundamental law of gearing will still be completely satisfied. This is not true for other conjugate gears. The other conjugate gears, if you have a slightly different condition during the assembly process, then suddenly you may see that the fundamental law of gearing may collapse, in which case the gearing arrangement will not be able to transmit a constant velocity ratio. Nothing of that sort happens in this case of involute gearing. Even if there is a small change in the shaft distances, then that can be accommodated with a slight change in pressure angle. I think you will appreciate this process a little better when I show you the next, in the next slide, the example worked out. The question is, what is the effect of pressure angle on power transmission? Pressure angle directly affects the torque. As I said, F times cosine of phi times Rp is the torque. So, the torque is directly proportional to the cosine of the pressure angle. Torque times velocity is the power. So, therefore, the effect of power on pressure angle is cosine phi. So, that is how it is understood. The next question is about coarse and fine pitches. So, when you say there is a gear is of a fine pitch, by pitch you usually mean circular pitch, it essentially means there are lots of teeth. When it is a coarse pitch, by coarse pitch you will mean the module is high, and by fine pitch you will mean the module is low. So, low module gears which are less than in the standards of SI, it is supposed to be 1.25 mm. When the module is low, that means module is d by t, diameter by the number of teeth. So, when the module is low, effectively it means the number of teeth is high, right. So, for the same diameter of the gear, if you have large number of gear tooths, you call it as a fine pitched gear, and the critical point seems to be as per standards is 1.25 in millimeters, right. So, if you happen to have more number of teeth, you are basically having a fine pitch gear. Okay, that is answered. In cycloidal tooth profile, if pressure angle continuously varies, then how can we use it in the design process with module? See, we are not going to get into the working of cycloidal gear. As I said, our scope here is mostly the involute gears. We are not talking about cycloidal gears simply because cycloidal gears are less useful in application. More prevalent, more widely used gears in applications are in involute gears. There may be very specialized applications where say they still use cycloidal gears, but the deficit of cycloidal gear definitely is that the pressure angle keeps changing. There may be situations where you do not mind that fluctuation in pressure angle. The fluctuating pressure angle may create fluctuating torque and fluctuating deflections also as a result. There may be certain applications where you just do not care about those fluctuating torque effects, and as a result you may still want to go with cycloidal gear. So, in effect, if the only thing that you are looking at is fundamental law of gearing, cycloidal gear may still provide a solution, but it is not a robust solution, which is why we are not and manufacturing that also has difficulties, which is why we are refraining from studying cycloidal gear in greater details. But please accept the fact that cycloidal gears also satisfy fundamental law of gearing. Even if the pressure angle continuously varies, there is nothing wrong in using nothing wrong in the sense of kinematics. I would say in the sense of kinematics, there is absolutely no problem, in the sense that it will still satisfy fundamental law of gearing and will be able to give you a constant velocity ratio. So, that is my answer to your question. This next question is apart from involute and cycloidal profile, is there any other profile that follow the fundamental law of gearing? Well, you can actually generate your own profiles. If you look at, for example, Ghoshan Mallik's book, he actually gives you a process by which if you specify one profile, the other profile can be generated. If you specify the profile of one gear, then what is the other profile that is required such that fundamental law of gearing can be ascertained. That detailed procedure is given in a book like Ghoshan Mallik's book in mechanism. But all that is, I would suppose, mostly for academic calculations and for theoretical reasons. Practically, what wins the race hands down among the different possible tooth profiles is involute gear. So, therefore, we are concentrating only on the involute gear. There virtually given any arbitrary tooth profile on one gear, you can generate the tooth profile on on the other mating gear such that fundamental law of gearing is satisfied. So, there is absolutely no restriction that in terms of fundamental law of gearing that only involute tooth profiles are the answer. Fundamental law of gearing never says that it is only the involute tooth profile which has to work. No, it simply says that only certain gear tooth profiles are allowed wherein the pitch point does not change during the course of engagement. It so happens that involute tooth profile on one gear is conjugate to the involute tooth profile on the other gear also, making it satisfy fundamental law of gearing. Similarly, true for cycloidal gear tooth profiles. Cycloidal gear tooth profiles are also conjugate, but you can have an arbitrary gear tooth profile. For example, you could have a straight gear tooth profile on one gear, but the conjugate to that will not be straight, that is for sure. You will have to determine the profile of the tooth for the other mating gear such that the fundamental law of gearing is satisfied. Okay, the next question is, can cycloidal tooth obey law of gearing? Yes, cycloidal tooths also obey law of gearing. The next question is, why only 14.5, 20 and 25 degree pressure angles are used? This is a part of standardization. standard gear manufacturers will manufacture gears only in standard pressure angles. These are the nominal pressure angles. Again, as I said, that if you have assembly related inaccuracies, the pressure angles will change. The nominal pressure angles under which the gear design and gear manufacturing has taken place under standard conditions or under the standardization processes are 14.5 degree, 20 degree and 25 degree. There is no rule that you have to have only these pressure angles. If you want, you can manufacture, if you have a manufacturing facility for yourself, you can manufacture gear for any pressure angles, that is not a problem. But please keep in mind that if pressure angle is large, then basically your torque transmission will have a hit, because torque transmission has a factor which is F cos phi. So, if you make phi large, cos phi comes down. So, therefore, even though you are transferring a large force, the torque transmission will be compromised, and similarly it will lead to a large axial deflection. So, the guideline is keep the pressure angle small, but you cannot I mean, if your question is why don't you have a pressure angle of, let us say 18 degree, you can have a pressure angle of 18 degree, there is absolutely nothing wrong in that, but because of the process of standardization, we wish to have not very many different types of pressure angles, but a few standard types of pressure angles, so that the mass manufacturing of these gears are made easy. Okay, the next question is how to cut an involute tooth profile. As I said, this class is not about gear manufacturing. If you wish to understand how involute teeth profiles are cut, please go for topics in gear manufacturing. But I will just answer your query in this fashion, that as to what I said is that one easy way to manufacture a gear would be take a rack which is basically a cutter, and that rack, if you oscillate to and fro on a gear blank, then as the rack oscillates, it will cut out an involute gear tooth profile in the case that we are interested in. So, this is one this is actually the principle involved in some of the gear manufacturing operations. There are other gear manufacturing operations, for example, there could be gear casting, gear milling and so on and so forth, but rack cutting operation is also one major way in which gears are manufactured. BMSC is asking which profiles are easy to manufacture. Obviously, it is the involute gear profile which is easy to manufacture, at least through a rack cutting operation. But if it is a gear casting operation, then it does not make a difference whether it is involute or cycloidal or anything else. So, as I said, there are many different processes of gear manufacturing. It so happens that the rack cutting operation is easier for an involute tooth profile. Involute and cycloidal profile, there is a difference in pressure angles. In fact, for cycloidal profile, I mean BEC is asking what is the difference in pressure angle between involute and cycloidal profiles. For involute, the pressure angle concept is well defined. For cycloidal, the pressure angle actually cannot be well defined because the common normal will change. So, the concept of pressure angle is fuzzy in cycloidal profile. I urge you to stick to involute gear tooth profile. If you look at the GATE syllabus also, the GATE syllabus concentrates predominantly on involute gear tooth profile, because by now we have realized that this is the most widely accepted gear tooth profile. As students, please understand one concept, the simplest concept, understand it easily. Don't unnecessarily clutter your mind with too many diverse issues and get confused. Understand the first concept easily and soak that inside yourself, and the additional details, if you require it, you can always then learn it yourself. One question that I have got is, why is that one gear has lesser radius than the second one? Well, if both the gears have the same radius, then actually there is no velocity increase or torque increase that you can attain with that transmission system. The purpose of a gearing arrangement is to make sure that you attain either a velocity scale up or a torque scale up, similar to a transformer in the context of electrical currents. So, there you have voltage and current being sort of stepped up and stepped down. Gearing is exactly the same thing, keeping the power requirement same. You wish to control the torque and the speed ratios, right. So, in case you want more torque when your vehicle is moving uphill, then you would like to go to a lower gear, and in case you want a higher speed, you want to go to a higher gear, right. So, as a result, if you have both the gears with the same radius, then obviously there is absolutely omega 1 will be equal to omega 2, torque from gear 1 will be equal to torque from gear 2. You will not get a gain either in torque or in terms of the velocity. So, you might as well do away with a gearing arrangement where the gears are having the equal diameters. So, therefore, it makes sense that one of the gear should be the gear ratio should be anything other than unity, which essentially means the gear sizes should not be identical. Okay, the last question that I have is, which profile has the least pressure angle? See, we are talking about involute pressure tooth profile. Involute tooth profiles can be made with pressure angle 14.5 degree, can be made with 20 degree, can be made with 25 degree. We are not actually comparing different tooth profiles at this stage. In fact, as I told you, it's difficult to make that comparison because pressure angle is not constant for other tooth profiles. Pressure angles happens to be constant for involute tooth profile, and for involute tooth profile, the standard pressure angles in which mass produced gears appear for are these pressure angles of 14.5, 20 degree and 25 degree. Okay, so looks like these are the questions we have at this point. So if that's all, we will go forward from here. Yeah. So next I have an example to you to demonstrate these calculations. So what I have done is I have taken an example taken from possibly Shigley's book. Yes, from Shigley's book. So here I have a 19 tooth pinion meshing with a 37 tooth wheel, and the gear module is taken as 4 mm and 20 degree is the pressure angle. So with this data, the first part of the problem is to find all the other dimensions, assuming them to be as per SI specification, and SI specification has already been given in this chart. So what I have done is I have made an Excel sheet. So here is the module 4 mm, the pressure angle is 20 degree, in terms of radians that is 0.35 radian approximately. So this is the data for the pinion and this is the data for the wheel. It is given that the number of teeth is 19 in pinion and the number of teeth in the wheel is 37. Wheel is, remember, the larger. So the larger gear will have the larger number of teeth also. This is as per the data. So from the formula that module is equals to d by n, or diameter by number of teeth, diameter of the pinion and the wheel can be computed as a product of module times the number of teeth. So I have implemented that. 19 times 4 is 76 and 37 times 4 is 148 millimeters, and the pitch circle radius is just half of that, which is as per this calculation. Circular pitch is pi times the module. So therefore both the pinion and the wheel have the same circular pitch. Gear ratio is the ratio of the two diameters, which in turn is the ratio of the two teeth also. So that comes out as 1.947 in this case. The center distance, as per the designer, when he says that the pressure angle is 20 degree, then he basically says that the centered pitch circle in this case should be such that it should be pitch circle radius should be 76 in one case and 148 in the other. So in such a case, the center distance between these two gears is supposed to be 112 right. So when we say that we have bought two gears of 4 module and 20 degree pressure angle, the expected center distance between these two gears is supposed to be calculated in this fashion, which turns out to be 112 And now for the other geometries, addendum, it is equals to 1 module as per the SI standard. So therefore it becomes 4 Dedendum is supposed to be 1.25 module as per the standard. So that becomes 5 and the hole depth, the addendum plus dedendum taken together, is therefore 9 for both the pinion and the wheel. The clearance, which is dedendum minus addendum, in this case is 1 again. The base circle radius, which is pressure angle cosine of the pressure angle multiplied by the pitch circle, is coming out to be 35.7 and 69.5 respectively. So this is the nominal dimension. This is the dimensions which is supposed to be present in the gears as per the designer's recommendation. Now, if due to assembly process the center distance is increased by 2%, what will happen is that the pitch circle will accordingly change, but the base circle will remain the same, because the involute that has been cut, the involute tooth profile that you are seeing on the gear, that suddenly cannot change if the assembly process has shown up a 2% inaccuracy. That is not possible. The involute tooth profile of the gear is supposed to be the same. So, if the involute tooth profile is supposed to be the same, the associated base circle which generated that involute is also the same. So, therefore, the base circle in any case will remain fixed. It is only that the center distance will have to be changed by 2%, but center distance, remember, is the sum of the two pitch circles. So, base circle cannot change, pitch circle has to change, and there is a relation between base circle and pitch circle, which means that the pressure angle also has to change. So, if the center distance changes by 2%, instead of 112 mm it becomes 114 mm, which can jolly well happen during the assembly process. This can be accommodated only through a change in pitch circle, but the pressure angle therefore also will be changing accordingly, right. So, what has happened here is 38 plus 75 is now going to become 114, and the pressure angle will be changed such that now 35 turns out to be 38.76 into cosine of this pressure angle. So, this new pitch radius multiplied by cosine of this new pressure angle will become the base circle. So, what I have actually used here is this formula. Rp1 plus Rp2 is equal to the new S. So, I will just do it here. So, we know that Rp1 plus Rp2 has to be the shaft distance, right, and we also know that Rp1 is equals to Rb1 by cosine of phi. The phi between the two gears is just the same. So, what we must have under all conditions is this: Rb1 plus Rb2 divided by cos phi should be equals to S. For assembly inaccuracies, Rb1 and Rb2 does not change, the base circle does not change. What changes is S changes to some value, let us say S prime, which in this case is 1.02 times S. So, therefore, if Rb1 and Rb2 does not change, then Rb1 plus Rb2 also cannot change. So, therefore, the only way in which this can happen is that phi also has to change to phi prime, such that S prime cosine of phi prime must be same as S cosine of phi. So, whatever is the nominal shaft distance multiplied by the nominal cosine of the nominal pressure angle, that, so the nominal values are available with us, we know what is the changed value of the shaft distance. So, therefore, phi prime can firstly be evaluated from this consideration. Once we get phi prime, we can put it back in this equation, and when we put that back in this equation, we will get the new pitch circle radius. So, all that has been done in this Excel sheet and the calculations are presented. So, what you see is that this 2% change in the shaft distance has increased the pressure angle by again a little more than 2 degrees. From 20 degree it has come to 22 degrees. So, it is actually quite a bit in terms of percentages, but you would really not matter a 2 degree change in pressure angle. Other than this effect that the pressure angle has changed, there is nothing lost in this process. So, that is why we say that the involute gearing is a robust mechanism, in the sense that it is able to accommodate any inaccuracies associated with the process of assembly. Okay, we will now turn back to our slides and we will now talk about the engagement process of the involute tooth pair. And for that, I will again go back to my model first before explaining on my slides. Okay, so let us take this one now. So it's exactly the same, but here just a few more illustrations are taking place. So as usual, you have two gears and we have cut only one side of the tooth of a single gear, right. So here is the engagement process that is taking place, right. So let us understand this situation. In this situation, the tooth pair is not in contact, there is no engagement. So I will hold this lower disc to be the driver gear and the upper disc to be the driven gear, right. So it is just that this discs have a lot of friction because they haven't been regularly used. So which is why I have to push this one also. But ideally you would expect that if I push this gear, which is what I am being able to get now, the other gear is being able to move. So if I am applying a torque here on this gear, you are able to see that the torque is getting transmitted. So let us understand at what point does the first transmission takes place from this gear to this gear. So the first transmission takes place at this point. And how do we identify this point? This point is identified where the extreme uppermost or the outermost periphery of this gear is just come in contact with this body. So wherever the addendum circle of this gear, this circle is the addendum circle of this top gear, you can see that this outermost periphery is tracing this white line, this addendum circle. Wherever the addendum circle of this gear is for the first time contacting with the tooth profile here, there you have the first engagement, right. So this is the first point of engagement. And where is it getting disengaged? It is still in contact, it is still in contact. Then from this point onwards, it is getting disengaged, right. From this point onwards, it is getting disengaged. And that point is the point where the addendum of this circle of this gear, the addendum of this gear is this circle, right. So the addendum of this gear, the last time when it is in touch with this driven gear is where the last point of contact happens. So the first point of contact happens when the addendum of the driven gear is having a contact with some portion of the driver gear. The last point of contact, or rather the point of disengagement, happens when the addendum of the driver gear is passing through the certain point of contact of the driven gear. So this is the last point of contact. So with this understanding, let us now come back to this drawing. So we have three different circles that has been drawn here. What has been drawn in green is the pitch circle. You can see the pitch circle are actually touching each other. It is in a condition of tangency. In blue, what has been drawn is the base circles. In red, what has been drawn is the addendum circles. So there are three circles in the driver gear and the driven gear that has been drawn. We know that the point of contact is supposed to be, for an involute gear, it's supposed to be resting on the internal tangent between the two base circles. So the point of contact, we are assured by our cross belt pulley analogy that the point of contact has to be on the internal tangent of the two base circles. There is no other option, right. But the engagement will actually start when the addendum of the driver gear is, the addendum of the driven gear is passing through this point of contact. So wherever the intersection, we have the intersection of the addendum of the driven gear, there we have the start of the engagement. Wherever the addendum of the driven gear intersects this tangent to the base circles, this happens to be the intersection of the addendum of the driven gear with the internal tangent to the two base circles. So this point is the start of engagement. Similarly, the point of loss of engagement or the point of disengagement is where the addendum of the driver gear intersects with this line, which is anyway the line in which the point of contact has to reside, right. So the intersection of the addendum circle with this internal tangent will turn out to be the end of engagement or the point of disengagement. So, start of engagement is the intersection of the common normal with the addendum of the driven, whereas the end of engagement is the intersection of the common normal with the addendum of the driver, and this line is called the length of action. So, we will come back to it when we talk about contact ratio also. So, now what we are going to understand is the concept of interference. So, let us go ahead and understand what is the concept of interference that happens in involute. Involute gears, by the way, have the disadvantage that the one disadvantage is this concept of interference. So, let us carefully study it. Now, you have realized that there are many circles that we are talking about in gears. There are addendum circle, there is dedendum circle, there is base circle, there is pitch circle, and so on and so forth. So, the two important circles which arises in the context of interference study is base circle and dedendum circle. So, let us once more look at that carefully. So, here we have shown two gears, and this figure is taken from Shigley's book again, and here we have the base circle which has been marked, the dedendum circle which is the circle which is passing through the bottommost point of the gear tooth profiles. There is a pitch circle similarly marked, there is an addendum circle similarly marked. So, base circle has a completely different concept as from the dedendum circle. Base circle, if you recall, is the circle from which the fictitious string was unwound to generate the gear tooth. The dedendum circle, on the other hand, was given by just the circle which is obtained by joining the bottom lands of these gear tooth profiles, and the formula for the base circle and the dedendum circles were also different. For example, the formula for the base circle was Rb equals to Rp cos phi, and the formula for dedendum was Rd equals to Rp minus dedendum, and dedendum was taken as 1.25 times the module simply as a rule of standardization. Right? We are not going to get into how it was derived and so forth. It is derived from stiffness considerations and strength considerations, but from standard formulas available in books of standards in gear design, we have picked up that the dedendum formula is Rb equals to Rp minus 1.25 times module. So, this leaves that there is a possibility that both the following conditions can happen. You could have a base circle which is larger than the dedendum circle. You could also have the case where the base circle which is smaller than the dedendum circle. So, this gives the leads to following interesting fallouts. We know that the involute profile is possible only in the radial portion extending beyond the base circle, because you cannot have the string to be unwinding inside the base circle. The string will unwound itself only in the region exterior to the circle, right. So, accordingly, the involute tooth profile can exist only beyond the base circle, not below the base circle. So, in case it happens that the dedendum circle is below the base circle, that means there is some portion that is precisely between the base circle and the dedendum circle, there is a portion of the tooth profile which is technically not an involute. It cannot be an involute because involute cannot be present in the portion which is below the base circle, right. So, therefore, what is usually assumed is that the portion below the base circle, in case you have the situation that base circle turns out to be larger than the dedendum circle, the portion in between the base circle and dedendum circle is simply a radial extension. It cannot be a involute. I will just explain myself once more in these notes. So, let us be clear on this, that there is a base circle Rb. From the same center there is a dedendum circle which just for the parameters that has been taken happens to be lesser than Rd. So, we are talking about a situation where Rb is greater than Rd. Now, when you say this to be the dedendum circle, that means the tooth profile has to extend up to the dedendum circle, but technically the involute cannot be present because involute is generated by unwinding a string from the base circle, not from the dedendum circle. That means the involute, whatever involute you generate, it has to finish at the base circle level, it cannot extend beyond the base circle. So involute cannot extend in this portion, right. So if at all there is a tooth profile, that tooth profile is not involute, right. So we take this to be just radially extended version of whatever happens here, right. So that radial extension causes a lot of problem, because now what you have is that if there is engagement happening in this portion is not involute. So as a result you will have lots of problems, and this is what eventually will lead to interference. So let us look at that aspect. Okay, so as I said that the involute tooth profile extends only in the region, radial region, which is exterior to the base circle, and the dedendum circle is radius is given by this formula as per standards. So we know that the base circle is pitch circle times cos phi. It turns out that if the number of tooth is 42 or more for a 20-degree pressure angle, then the dedendum circle is always greater than the base circle, which means that the gear tooth has ended before the base circle, right. The tooth profile does not extend all the way up to base circle, it is actually terminating well before that, because dedendum is the level at which the tooth profile is ending, and the base circle is lower than that. That means the tooth profile has actually ended beyond well above its limit, which means the entire tooth profile is an involute. So no issues associated with this situation, but see the number of teeth that is required to attain this condition is actually pretty high, it is 42. You have to go for at least 42 number of teeth in a gear to ensure that the dedendum is always greater than the dedendum circle radius is greater than the base circle radius. If you have the situation where the number of teeth is 41 or lower, then there is then it can be proved that the dedendum circle radius is actually lesser than the base circle radius. So in between the base circle and the dedendum circle there is a region where the tooth profile is not involute, and as a result this case deserves some special attention, because if you do not have involute tooth profile, for one thing you will not be able to satisfy the fundamental law of gearing. So as we said that in this region which is falling below the base circle region, we simply assume that the tooth profile is radially extended, but this leads to some problems as we will see. The engagement between the tooth profile should be in the involute for conjugate action, but this conjugate action is denied once we have this situation that it is for a 20-degree pressure angle, number of teeth less than 41, you will not be able to satisfy this condition of conjugate action if the if there is a engagement happening in this portion which lies between the base circle and the dedendum circle. Okay. So if the engagement of the wheel with the pinion is in the region below the base circle, then there will be an interference, because conjugate action is not going to happen. Conjugate action, by the way, simply means the action of engagement between two gear tooth profiles which satisfy the fundamental law of gearing. If fundamental law of gearing is not getting satisfied, conjugate action is denied, then there is a possibility of interference, which is what we will study. So let us look at this condition carefully. So we already know that the engagement happens in between this region which is called the length of action. So the length of action is this line AB, which is basically the tangent between the two base circles. Again, what is drawn in red is the two base circle, what is drawn in blue are the two pitch circles. I have only indicated the addendum circle of the larger gear. By the way, interference will first happen in the pinion and then it will happen on the wheel. So the critical condition happens to be the interference on the pinion. So therefore the interference on the pinion is schematically illustrated in the drawing that you see. So what we must ensure is the fact that even if there is a portion of the gear tooth which is not involute, we must ensure that the engagement never happens in that portion. The engagement happens in the portion where the gear tooth is involute by construction. But the involute, as I said, will not be maintained in the portion only below the base circle. In the region between the base circle and the dedendum circle, this will be denied. So, we have to ensure that the contact never takes place in that region. If that can be sort of ensured, then we will avoid this perplexing condition of interference. So, we will analyze what that condition boils down to. So, we have already seen that the engagement or the point of contact between the two gear tooth will have to stay on this line AB, but it does not necessarily has to extend all the way between A to B. It has to extend only up to the points of intersection of the addendum circle radius. The two addendum circles, wherever it crosses, as we had seen in the few slides upstream, wherever the two addendum circles intersects this line of action, that is the point of engagement and disengagement. So, what we have to make sure is that the two addendum circles never fall outside the intersection of the addendum circle, never cross this point A, or from the perspective of the pinion, it never crosses this point A. So, this is basically the critical region that it should, the addendum of the mating gear should not cross this point A. If it crosses, then it will not see a involute action, and therefore, there will be interference. So, for interference at pinion to start, and this is the condition of the interference at pinion, the addendum circle from the other gear, that is the wheel gear, will be at O2A. So, here you see that the addendum circle has just crossed A, right, that point A. Typically, what you would like to have is that the addendum circle should intersect this line AB at an interior point rather than at the extreme point of A. But the way we have drawn this figure, it is just the start of interference, where you see that the addendum circle has actually intersected the line AB at the extreme point A. So, if you work out the geometry now, what you can do is you can consider this triangle O2AP, and using the cosine triangle rule, you can find out that O2A square, which is sort of this distance O2A square, will be O2P square plus AP square plus 2 times product of this distance, rather minus product of this distance into cosine of the angle between AP and O2. So, cosine of the angle between AP and O2P is pi by 2 plus phi, because this is a 90-degree angle plus phi. So, this is pi by 2 plus phi is the angle between AP and O2P, right. Our cosine triangle law says that O2 square plus O2A square is equals to O2P square plus AP square plus twice the product of the two distances, or I should correct myself, the square of the sum of the square of the two distances minus product of the two distances into cosine of the angle embedded by those two other sides of the triangle. The angle embedded happens to be pi by 2 plus phi. So, cosine of pi by 2 plus phi is actually sine of phi with a negative sign. So, therefore, using those simplification, you actually get a plus sine phi here. So, I have omitted a step in between and just given you the final result. So, the final result is this, and again AP, this is AP. If you look at this triangle now, O1AP, this is a right angle triangle because O1A is the radius of the base circle, AP is the tangent to the base circle. So, therefore, AP has to be equals to O1P sine phi, because this 90-degree will also be equal to the angle, this angle phi will also be equal to the angle between O1P and AP. So, therefore, AP will be O1P into sine phi. So, with this now you can do the following simplifications and get O2A square to be this formula. This is just I have plugged in the value, the formula for AP here, and I have taken out O2P square as common, and therefore, you get a formula of this kind. So, in the next step what I do is, here I take a square root on both sides and derive what is O2A minus O2P. So, O2A minus O2P, O2A is the addendum circle radius, O2P is the pitch circle radius. So, O2A minus O2P is basically the addendum, and that boils down to this formula, right. Now, if I recall that the from the point of view of SI standards, what I have shown, addendum has got to be equal to 1 module, right. So, addendum which is equal to 1 module, by definition, that is diameter by number of tooth. Diameter is 2 times O2P, because O2P is the radius and the diameter of the pitch circle is 2 times O2P. So, we have the addendum to be equal to 2 times O2P divided by N2. So, we introduce this terminology of gear ratio, which is lambda, which is the ratio of the two gear sizes, which because of the fact that the modules are same, is also the ratio of the two ratio of the two number of teeths present in the two gears. So, N1 is the number of teeth present in gear 1 and N2 is the number of teeth present in gear 2. So, N1 is equals to lambda times N2, that is as per our notation. So, therefore, to avoid interference, we must have the addendum to be lesser than what is depicted in this picture. This is just the maximum that you can go where the interference has just started taking place. So, if the addendum is lesser than what this picture and this analysis suggests, then the green circle will pass through an interior point, and if it passes through an interior point, then the engagement will actually end somewhere here, which means that the engagement will end in the portion which is above the base circle of the pinion, right, and that will essentially mean the engagement happens only in the involute portion of the gear tooth. We understand that there is a portion which is not involute, but that portion the engagement never happens. So, we need not worry about the consequences of that wrong engagement. So, therefore, the technical condition of interference boils down to the fact that the addendum must be less than what we have computed for the critical situation where the interference just occurs. And now, if we put back these values of addendum as 2O2P by N2, and on the right hand side we have already derived this expression, this is what we get. And finally, therefore, we will firstly get N2 to be greater than certain number, but then N1, which is the number of teeth on the pinion, will be given by lambda times that, and that works out to be this formula. So, in other words, we have what we have found is that the pinion must have a minimum number of tooth, and if the pinion has this minimum number of tooth, then you are sure that the interference can be avoided. So, this is something that arises not from the strength considerations, but from the kinematic considerations. That is why we are doing it in this course, because this course is about kinematics of mechanisms, theory of mechanisms if you may call it, and therefore, this is a kinematic condition rather than a strength related condition. And what we are left with is a formula which enables us to ensure that once we satisfy the minimum number of teeth in our gear as given by this formula, we will be able to guarantee that there will be no situation where the engagement is taking place in a portion where the involute action is compromised. Then even if the involute profile is not complete, certain portions are not involute, the engagement never happens in that portion, and as a result one is saved from the consequences of interference. Okay. A very related process is that of undercutting. As I said, one very common process of gear manufacturing is that of a rack cutting operation. So, rack cutting essentially means that it is an engagement of a rack cutter with a gear blank, right. So, we have to now boil down this situation to that of a rack and pinion gearing arrangement. So, just like what we have shown here is the interference between two gears, there is a similar condition of interference between a rack and pinion, but instead of deriving it afresh, which can also be done and that is also presented in certain books, what we will do is that derive the condition of interference as a in rack and pinion arrangement as a special case of this formula, which we have already derived. That can be done because we have already seen that if the wheel radius is assumed to go to very large values and mathematically infinite, then technically that boils down to a rack and pinion arrangement. If one of the wheel radius is made to approach infinity, then basically we get back the rack and pinion condition. So what we will do now therefore is that this minimum teeth criteria, we will now apply this limiting condition mathematically and will straight away get our rule for the minimum number of teeth that must be present in a gear such that the rack cutting operation can be done in a nice manner without defying the laws of fundamental law of gearing. Because if in a rack cutting operation now the fundamental law of gearing is sort of compromised, then not only will the gear I mean the gear produced at that in that instance will be weak in the sense that the interference aspect that we have been talking about from kinematic consideration will now lead to a strength deficiency, because the material will be taken out, because as you know the rack cutter will be a hard and abrasive material. It will scoop out the material from the base of the gear tooth and will result in a gear tooth which is weak, and therefore it will have such a gear tooth will be vulnerable to failure. So if there is interference between rack cutter and gear, then the gear material will be undercut, which means that material will be scooped out by the rack cutter from the gear material. So undercut gear tooths will be weak and will cause premature failure. So basically what we do is that we take this ratio lambda to be 0. Remember, lambda is the ratio of the diameters of the smaller gear to the larger gear. The larger gear in this case is having the dimension of infinity, so therefore lambda will become 0. So if we take that limiting condition into this formula, what we will get by application of L'Hospital's rule is this, that we will get this formula 2 by sine square phi. So the minimum number of teeth which must be given in a gear such that the rack cutting operation can be done without any cause of interference. The interference in a rack cutting operation leading to undercutting of the teeth, in that case the minimum number of teeth which has to be prescribed on the gear is got to be 2 by sine square phi. For the value of phi, which is about 20 degree, this number comes out around 18. So minimum 18 number of tooth must be there in a gear such that it can be manufactured accurately using a rack cutting operation. Else if you have a gear with very small number of tooth, then those gears will actually be undercut. In the tooth region the material will be lesser, and as a result the gear tooth will be weak. And also what you can see now is that if the pressure angle is large, then what will happen is that the sine square phi term will be large, and then the minimum number of teeth in the gear tooth to avoid undercutting is reduced. So that means the limit can be relaxed. So therefore pressure angle, in this sense pressure angle is helpful in terms of interference or undercutting, because if it is 18 with a 20 degree pressure angle, then if you work it out, let us say for 25, this number will be lesser, could be 15, could be 16. I have not calculated that, but you can do that. But one thing is for sure, that the minimum number of teeth for a 25 degree pressure angle gear will be lesser than the minimum number of teeth for a 20 degree pressure angle, and as such the requirements will be less stringent, and in that sense pressure angle is helpful in reducing the requirements in terms of undercutting. But as we said, if you have a large pressure angle, then there is large amount of wastage in terms of torque transmission, and also it could lead to axial deflection. So you will have to take care of all that and arrive at a compromise value of phi, and all this has been worked out, which is why we say that as per standards the pressure angles are one of those numbers, 20 degree, 25 degree or 14.5 degree. Okay, I think we will keep it till here at this point. In the next few minutes that is available, I would like to keep myself open for any questions or interactions that you wish to have. Okay, DCHY is saying whether sliding will happen in gearing action. Sliding does happen. There is absolutely no reason that sliding will not happen. At the point of contact you do not have the no slip condition. No slip condition will happen only when you know the point of contact is the pitch point. But when the point of contact between the two gear tooth profile is not at the pitch point, then there is a relative sliding that is there. So as I said, it is not require this mechanism of gearing uh, works not on the principle of friction, right. It is perfectly permissible to have a sliding between the two surfaces, which is why it is a higher pair mechanism. In a higher pair mechanism, you do have sliding as well as rolling without slipping. It is only in a friction disk where we take this approach that there is no slipping possible at the point of contact. But in the case of a gear tooth engagement, at the point of contact, if the point of contact is anywhere other than the pitch point, then there is relative slipping between the two gear tooth profiles. I hope I have answered that question to you. GGIPGB is asking why we prefer involute over cycloidal profile. I think I have talked at great length over that. So please look back at the video and you will be able to see what are the advantages of involute tooth profile. So these are the advantages of involute tooth profile. Other than the first aspect, cycloidal tooth profile doesn't follow have any of these advantages. It may have other advantages which I have not talked of here, but these are very important advantages of involute tooth profile, which makes it a winner in terms of mass production of gears. So that's why we have involute tooth profile. Okay, someone is asking if there is no interference in cycloidal profile, why should we use involute profile? Well, it's your choice. If you still want to use cycloidal profile, go ahead. Some of the disadvantages of cycloidal profile being that it will not be smooth in operations, it will have some dynamics associated. Some of these advantages that you get in involute tooth profile are actually very big advantages. You are right in saying that involute tooth profiles are compromised for interference from the perspective of interference, but then interference can always be avoided if you stick to the simple criteria of minimum number of tooth. So that's why we have studied interference, because if you abide by this condition of selecting the minimum number of gear tooth as per this law, then interference can be very effectively avoided in case of involute gearing. So the fact is, if there is a deficiency in involute gearing, that involute gearings are prone to interference, but that deficiency can be addressed very simply by using this formula. So I would rather suggest that use this formula and get rid of the deficiency associated with the involute gear, rather than selecting a cycloidal gear which is prone to other deficiencies which are difficult to correct, right. So as I said, there may be certain applications where you may not be so very worried about dynamic deflections of the shaft and etc. In such cases, you go ahead and use cycloidal profile if you want to, but the fact of the matter is, the world around you is working with involute gears. You will do well to appreciate that fact and also work with involute gears. They are the ones which are being mass produced, not cycloidal gear. If you want, you can make a cycloidal gear in your own workshop and use it for whatever applications you think is permissible for cycloidal gear. Okay. Next question is about how can we control interference if there is vibration between the two shafts. I think this question is outside the purview of the present course. Vibration of the shafts is got nothing to do with the context that we are dealing with. Obviously, vibration of the shaft makes it very difficult. It's difficult to control directly this vibration of shaft. There are lots of active research work that is going on. This is well beyond the purview. This question is well beyond the purview of the course. But what I can tell you is that you can still do analysis. Together, what typically we do for our research is that we take gears mounted on shaft and try to take the vibration and the dynamics of the gear together with the shaft. In doing so, we can analyze under what conditions there will be large vibration and under what conditions there will be less vibration. So each of these conditions have to be determined on a case by case basis, and that's why there is no clear rule that using this rule using a formula of this kind you will avoid interference. This formula has been arrived at from perfect rigid body dynamics and kinematics consideration. There is nothing about shaft deflections that has been used in this formula. Okay, what is the reason of interference in involute gear? VCE is asking. I think that's exactly what I have talked. In case you have not understood, I will request you to look back at the video itself. The videos will be posted by the technical team as soon as the class gets over. Please look at it. For the last 30 odd minutes, I have been explaining the reason of interference for the involute gears. So look back at the lectures. Hopefully you should be able to grasp it if you relook at the lectures. Okay, regarding the books, I think as I said, there are many books and references on this topic, but what we follow at IIT Madras is usually this book by Ghosh and Malik, titled Theory of Mechanisms and Machines. And accompanying the book, you will find Professor Malik's lectures in NPTEL website. Also, Professor Ghosh's lecture on dynamics of mechanisms are there. So, though this course is I mean, this part of the course, the gears module is more specifically tied to the kinematics part. So, if you are looking for some supplementary material on the gears, I would strongly recommend you look up these videos by Professor Malik. You can also look up at the book. Norton's book is a pretty standard book in internationally acclaimed. It is a little more verbose in its content, so it sort of deals in very elaborate details each aspects, some of which we have talked about. Professor Shigley's book is also available, which is also very internationally acclaimed, and the problems in Shigley especially are nice and smart. So that's also something that I will encourage you to. But my advice to you is to go with one book and try to assimilate and digest the contents of one book rather than to dabble with 3 or 4 books and not attaining a complete knowledge from any one book. Okay, so after attaining a satisfactory level of understanding from one book, you please go ahead and look at other books if you want to. But what cannot be compromised is that at least one book you should be able to read. Professor Ghosh and Professor Malik's book obviously does contain certain advanced materials which typically is not there in an undergraduate course, or even for that matter in the GATE syllabus. So it does contain certain additional stuff, but you can refer those parts which, let's say, I have taught to you, and these parts mostly cover in entirety the GATE syllabus, which is like a benchmark standard. So you will do well to do that. You could also look at Norton's books or Shigley's book. They are all pretty much at the same standard. There are other books also available in the market. Some of them I may not be aware of, but these are my favorite books. I will very strongly recommend you go through this YouTube channel of Ujjwal Rane, not only for the gears but also for the other mechanisms, the different slider crank mechanisms and its inversion. They have been very nicely elaborated together with the visualization aids, because visualization aids will be very important for you, especially in the learning stage, to get a flavor of the subject. And once you get these visualization ideas correctly settled in your mind, you should be able to do the analysis even more comfortably. So therefore, I conclude this class today. I look forward to the next class in which is due. That's the third and the final lecture session. Thank you.